Okay, so we are going to look at a specific ring. We're going to look at the ring of polynomials over F2. So the coefficients are 0 and 1. And we're going to look at the ideal generated by x squared plus 1 in F2, adjoint x. And we are going to try to understand the arithmetic of the quotient ring. Okay. So let's do exactly that. Let's first notice that when you have so what is one way in which you can try to understand a new structure? Well, you can write out like the multiplication and the addition tables. But to do that, you kind of have to have a list of elements if there are finitely many. So let's notice here that, well, if I have like a high power of x, say x to the fifth, I claim x to the fifth we can rewrite as like x times x squared squared. And the reason why we might want to do that is x squared plus 1 plus I is equal to I. Why is that? Well, x squared plus 1 is in the ideal generated by I. So if I add it in, nothing changes. Now, if we were to sort of subtract 1 from both sides, but subtraction and addition are the same in F2, we get that x squared is the same as 1 plus I. X squared plus I is the same as 1 plus I. Great. So what this is saying is in the quotient, we can replace all of our x squareds or higher. This is like an or higher term with ones. So if we were to look at, for example, x to the fifth plus I, well, as I've written, that's x times x squared squared plus I. But x squared is 1 mod I. So we get x plus I out of that. So this means then any element, I'm just going to let R be the quotient, where we take F2 adjoint x, and we mod out by x squared plus 1, can be sort of reduced to a polynomial, but it's not a polynomial, it's just like a polynomial expression, of degree 1 or less. Because if you had degree 2 or more, like for example x to the fifth, you can do these tricks where you pull out a certain number of x squareds and you replace them with a 1 in this ring. So if we were to just list the elements of our quotient ring, of this new ring we're constructing, well, we could have 0, certainly. I'm gonna not write the x squared plus 1, just because that's a lot of, as you can tell, it's a lot of plus i's and stuff. We would have 1, we would have x, and we would have x plus 1. And since our coefficients can only be 0 and 1, and everything reduces to something of degree 1 or less, this is all possible combinations, because you have 2 choices for the constant term, and you have 2 choices for the linear term. 2 times 2 is 4. We've listed all of our 4. All right, so this is really, just to be clear how we're viewing these elements, they're in the quotient. So I'm not writing the plus part because it would be a lot of plus x squareds plus 1s everywhere. So let's look at the addition table then here. All right, 0 plus 0 is 0, 1, x plus 1. This is, all normal. 1 plus 1 is 2, which is 0. 1 plus x is x plus 1. 1 plus x plus 1 is x plus 2, which is x. X plus 1 is x plus 1. X plus x is 2x, which is 0. X plus 1 is 2x plus 1 is 1. And then we'll fill out the rest. X, I think we get 1 here, and then I think we get 0. So that's our addition table in this ring. Now let's work on our multiplication table. Let me put a divider here. And this is where we're going to have to do a little bit more thinking, because really this is just the regular addition on the left. But now with multiplication, we're going to see some interesting stuff happens. So 0 is still the great annihilator. annihilates everything. And 1 is still the multiplicative identity, so it leaves everything alone. Now we have to fill out this remaining square. So let's do some work. The first guy in that remaining 2 by 2 square is x times x, which is x squared. I'm going to write a 3 equals just to indicate this is not happening in polynomials. And x squared is congruent to 1 we saw, so that's a 1. Weird, x has a multiplicative inverse. It's 1. Interesting. All right, let's now look at x times x plus 1, the next one. So that's congruent to x squared plus x, and x squared is the same as 1, so that's 1 plus x. So x times x plus 1 is also weird. We get that x plus 1 times x is x. And it's commutative, or sorry, it's x plus 1, and it's commutative, so this is also x plus 1. Now let's look at x plus 1 squared. So x plus 1 squared is, well, this is over f2, so the freshman's dream holds. There's no cross terms. And x squared is equivalent to 1, and 1 squared is 1. And 1 plus 1 is 2, and that's 0. So here is our ring structure, at least the multiplicative part. We have that x is invertible, but x plus 1 is not invertible. In fact, x plus 1 times x plus 1 is 0. So this is saying that x plus 1 is a 0 divisor. So as just a reminder, how do we understand rings? Well, we work out the addition and multiplication table, and this is what we get in this case. So as an example, which we'll do maybe in class, but you can think about now, what are the addition and multiplication tables for f2 adjoint x mod x cubed minus x minus 1, and as a hint, one way in which we think about this is when we mod out by x cubed minus x minus 1, it kind of means that x cubed minus x minus 1 is now 0. But it doesn't really mean that. It means that it's congruent to 0. And so what that tells you then is that x cubed is congruent to x plus 1. So what that is saying is, whenever you have something of degree 3 or higher, you can replace it with an x plus 1. Okay? So that's how you use, at least in polynomial rings, how you manipulate things in this quotient, manipulate elements in this quotient ring. You use the principal generator to tell you how to replace powers. So you can try out this question, and it's something we'll probably visit in class.